All right, kinematics in 2D. So in real life, you know, there aren't really a lot of examples of 1D motion. You know, I don't know, they're pretty boring. So things like an apple falling from a tree, which Newton knows about, apparently. A car driving on like a really straight highway. You know, on just a single street, which is sort of boring. I guess an elevator. We could study an elevator. That's 1D motion, unless you're in what are those sideways, like the Luxor in Las Vegas. Everybody go to Las Vegas? No. Every time I ask you guys a question, do you do this? It's blank stares. You should make a list, things that I must do in the next year. It's rock climbing, bungee jumping, skydiving. What do you mean no? Go to Las Vegas? Oh, yeah, we'll do that one. No chance of death in Las Vegas. All right, so where was I going with that? There's an elevator at the Luxor, which is the Pyramid Casino in Las Vegas. It goes on a diagonal, so it's still 1D motion. I've never ridden in it. I tried to sneak on, but it does go somehow on a diagonal. I don't think it does this. That would seem weird, but it goes like this. The Great Glass Elevator, right? Willy Wonka's great. That thing went in two. All right. Anyway, so there aren't a lot of interesting examples of 1D motion in real life, but there are lots and lots of examples of 2D motion. Hence, we spend some time studying them. So we're going to do a home run problem. So who's your favorite baseball player? Paul Konerko? White Sox fans? No. Hits a home run? That's another thing. Become a White Sox fan in the next year. Let's see. What's that? Yeah, I know. At least in 2005, we won one of them World Series things. Or they won, not we, they. Professor drives Mazda 3 to work. All right, I did have the car driving on a street, but that's 1D motion. Real cars drive pretty much in 2D. I'm going to quantify that, though. So I use the car. When you're driving a car, I call that 2D motion. Would you guys agree with me, or would you disagree with me? I can't get comfortable in this room. I'm sorry. My foot gets stuck. 2D motion. Why would it not be 3D motion? Well, if you're going up and down hills, right? So, you know, there are hills, so you move in both, let's say, the north, south, east, west directions, but you also move in altitude a little bit. There's hills. But really, it's we could say it's 3D motion technically, but compare the distance that you travel horizontally to the distance that you travel vertically. All right, which one's larger? The horizontal distance. All right, you know, at most you're changing, 100 feet here and there in hills, but you're traveling miles and miles and miles, so tens of thousands of feet, hundreds of thousands of feet when you're in a car. So really, you know, the vertical direction is so small we don't care about it. So it's really 2D motion. All right, Devin Gardner evades a bunch of tackles. Another example of 2D motion. Things like that. So the nice thing is, though, that the rules that we've learned already, so the rules for 1D motion, they apply. All right, so we're not really learning anything new. We're just learning a new application of stuff that we've already dealt with. Okay, so let's preface this by remember that you can write a 2D, how you write a 2D vector. Vectors, they have two components. In 2D space. All right, so but the reason that this is going to be a little bit more complicated is because now we're really dealing with vectors. When we're dealing with 1D motion, yeah, things were vectors, but you know, a vector in the sense that you could go that way or you could go that way. There were only two options. All right, it was a whole bunch simpler. But now we got to get back into remembering and becoming more and more comfortable with our vector notation. All right, so vectors have two components, an x component and a y component, if that's the coordinate system that we're going to use. And of course, we're dealing with vectors, things like velocity, things like acceleration, and all of those vectors we can write in terms of their vector components. So you're going to have to start doing that, breaking things up into the component stuff again from chapter 1. Okay? Now, in most cases, in most examples of motion, all right, motion in one dimension is independent of motion in the other dimension. So in other words, the two dimensions, I should say, motion in each dimension is independent. All right, so if you have something that's traveling horizontally, the motion, the speed, the acceleration in the horizontal direction does not affect the speed and the acceleration in the y direction. Okay, so they're two independent, the motion is independent. What that means then is that we can take a single 2D problem and break it up into two 1D problems. All right, and so in that sense, solving 2D kinematics problems is not really that much more difficult. Yeah, maybe there's an extra equation to solve, but the idea is exactly the same as the stuff we just did last week. Okay? So to illuminate this, let's start off with sort of a straightforward example. Hooray, example. All right. So the example is this. A boat. You get a boat traveling to China. Is that right? That does not look right. We're gonna go with it. San Francisco. That's right. All right. So a boat leaves China, or a boat heading to China leaves San Francisco at 5 meters per second, and it's traveling in a direction 30 degrees north of west. I want to know how long does it take to go 1,000 kilometers straight west. All right, so we're just dealing with a boat here. So the picture looks like this. There's my boat. And it's heading in this direction, right? At some velocity, 5 meters per second. And I gave you 30 degrees north of west. So 30 degrees is that angle. Okay? Now the question is, I want to know how long does it take to go, just straight west? Not northwest, but straight west. Right? So yeah, its motion is northwest, and we could sort of analyze the motion in the northwest direction, but if I want to break this up into how far does it go north versus how far does it go west, that becomes a 2D problem. Okay? Now, one of the ways I could solve this is we could try to write like a vector equation. In other words, I'd write something like x minus x naught vector is equal to v vector times t. Perfectly acceptable equation. That's like our fundamental definition of velocity right there. It's a vector, that's fine, but I don't really know how to solve that without doing another step. There's not, because vectors don't add, like normal numbers, so I have to do something else in there. And the only way that I can solve that is to, break the vectors up into their components. So really, this one equation, this is really, it's actually two equations. It's a set of two equations because we're in two dimensions. All right, so, implicitly in that equation, in that vector equation, is actually two equations. So really what we see is we have an equation for the west direction, which I'll write as x minus x naught is equal to vx times t, where I've defined this to be my x direction. All right, and if I define this to be my y direction, then I can write down a north equation, which looks like y minus y naught is equal to vy times t. All right, very similar equation, I just swap out x's for y's. Okay, so there are the two equations that I need to solve. Who can tell me, what's the first thing you have to do to solve this problem correctly? First step. I've already drawn the picture, that sort of thing. All right, so whenever we're dealing with 2D motion problems, you're going to have to deal with components. So the first thing you need to do is break up the velocity into its x and y components. So we're looking for the x component of velocity. All right, remember, we'll go back to trig. Now here's our triangle. If I draw in the triangle, I'm dealing with something like this. This is my vector triangle, or that's a right angle. I know the hypotenuse. I'm looking for this side, and I'm looking for that side. All right, I know 30 degrees. I know the hypotenuse, so I can find all of those things. So Vx then, I can solve that. I can solve for that given that my vector velocity is 5 meters per second. Vx is adjacent to the angle 30, so I'm going to use cosine of 30 degrees. All right, so you can solve for that, and you should get 4.3 meters per second west. I can solve for the y direction using the exact same technique, 5 meters per second. Instead of cosine, I use sine. And you'll find that the speed in the y direction is 2.5 meters per second. Okay? Now in this particular problem, I don't actually need the y component of the velocity, because I'm just asking about the displacement in the x direction. So I have enough information here with my 4.3 meters per second to solve this. All right, so I know delta x, I know Vx, I'm solving for t. So I can solve for t pretty quickly. It's equal to x minus x naught divided by v sub x. I know that the numerator is 1 million meters. I know the denominator is 4.3 meters per second. Meters divided by second is second, so I have the right units. And if I solve that, I should get 2.3 times 10 to the 5th seconds. All right. However many hours, I don't remember, but that's roughly 3 days. All right, so that's how we solve the problem. 2D problems. We break things up into components. We use some equations that we know and love. Plug and chug. All right, so let's sort of beat that point home just a little bit and talk about the equations of 2D kinematics. I shouldn't even bother to write all those down because they should all look familiar, but I just want to sort of beat home the point that you're dealing with the same questions just in two different directions, okay? Nothing else is different. So we're just going to spend the rest of today and then part of tomorrow talking a little bit about another special class of 2D motion. All right, now just like in 1D we talked about free fall, well, in 2D motion the analog to free fall is called projectile motion. All right? Projectile motion is sort of a special case, but it's very, very, very common. Just like in when we talked about free fall, if you ignore air resistance, All right, then objects. Objects, so this applies for objects that are moving at low speeds. I should say dense objects. This is what I said for free fall. I'm going to put that in parentheses. All right, if you ignore air resistance, which are objects, dense objects moving at slow speeds, then there's a simple solution to bodies that are moving through the air near Earth's surface. So, simple solution. All right, so that simple solution is simply stating that you have you have motion under a constant acceleration. Now in 2D, we have two possible accelerations. We have an acceleration vector that has two components, an x component and a y component. Now typically when we're dealing with projectile motion, which is, motion through the Earth's atmosphere kind of near the surface, we tend to define up and down as the y direction, and then left and right as the x direction. So tell me about the acceleration in the y direction then. If we ignore air resistance, what's the acceleration in the up and down direction for an object flying through the air? It's just g. All right? It's g, and it's pointing downwards. All right, if you ignore air resistance, what's the acceleration in the x direction? It's 0, right? What else is causing it to accelerate? It doesn't, if you're just talking about like a ball, a projectile, a ball or a rock or a pen or whatever, it doesn't have like engines making it accelerate in the x direction. The air isn't doing anything, so we're ignoring air resistance, so there's nothing causing it to accelerate, so the acceleration is 0. Okay? So that makes life really easy because, well, it's sort of like the problem we just did where we didn't have an acceleration in the x direction, it was simply in the y direction. And that makes our motion much, much easier to solve for in the y direction. All right, so to summarize that, the horizontal motion is easy to predict. All right, but the vertical could be a little bit more tricky. So now seems like a good time to sort of summarize my problem-solving strategy and the one that I'm trying to highlight as we've been solving these example problems. So hints to solve the problems, tricks, whatever you want to call them. Draw a picture. List what you know. And what you don't know. If you can, then break initial values into components. And then you can note a couple things, or at least you can note one thing. At the peak of the trajectory, we know something about the y component of the velocity. So imagine that you have like a ball that starts somewhere and goes and is thrown as a projectile. It goes up and then comes down. So this is just a picture of x and y. All right, what do I know about the y component of velocity at the peak? Exactly. So right there, Vy is equal to 0. And I'll restate it there. All right, so you can note that and maybe pertinent to your problem. And then you can go ahead and solve. I guess I should note a couple other things. So an object that starts and ends at the same height. All right, so you have an object that goes like so, and then ends right there. All right? We know that the velocity at this point, the vertical velocity at that point is 0. How does the time that it takes to go from here to here compare to the time that it takes to go from here to here? In other words, how does the time it takes to go from the initial position to the peak compare to the peak to the final position? The end at the same height. All right, they're the same. T up is equal to T down, which is equal to 1/2 T total, I'll call it. All right? Also, what can you tell me about the vertical component of the velocity initially compared to the vertical component of the velocity at the end? Close. Yeah, exactly. All right, so they're just the opposites. They have the same magnitude, but they're the opposite. They're the opposite. So the velocity as that thing passes, as it ends up at the same height, has the same magnitude.